Okay, thank you. Thank you for the possibility to speak here. Thank you to the organizers. I'm Marco Leonetti. I come from the CNR Nanotech, Institute of Nanotechnology. And the result I'm presenting here are in collaboration with in the labs of Italian Institute of Technology, Center for Life Nanoscience in Rome. So over there we have several research lines focused on optics, ranging from direct laser writing nanofabrication to physics of neural networks studied with calcium imaging. Here I'm going to speak about all optic and computation because we are presenting a technology which enables to compute the dynamics of a spin glass exploiting optics. So the talk is about all optical computation, and in particular it is a talk about glass. So this is because we are going to simulate glass dynamics. So we all know the glass is a structure, a solid system, which has a microscopic level disorder of atom location. So in this very nice slow-mo, you can see the cracks which are appearing at different location, different position in a glass which is hit by a bullet, and you see that the position of the cracks is completely random, and this is connected with a signature, the fact that at a microscopic level you have disorder organization of atoms. So we all know the fundamental states of matter: gaseous state, liquid state, and crystalline states. So the glass states is something in between the liquid state and the crystalline state. So actually, this is due thanks to the quenching. So you have you take a liquid and you drop the temperature very rapidly, and you have that atoms are frozen in a disordered configuration. So you have at the same time for this glass mechanical rigidity of solids and disordered arrangement of liquids at the microscopic level. So glasses are a mystery, and this is because many of the properties of glass are still unknown. This mystery dates back to the experiments from the early years of Royal Academy of Science in England, and you have, for example, the Prince Rupert drop that is nothing else than a piece of silica at the liquid state, which is rapidly frozen in a cool water. And you have this drop-like piece of glass, and you see that the head of the glass is incredibly strong in this slow-mo video, and this can actually destroy a bullet. On the other hand, when the shock waves arrives to the tail of the glass, this breaks the glass because the fragility is completely different and destroy completely the bullet, the drop. So this is connected with the residual tension in the glass structure that make the rigidity of the system incredibly strong at the head of the glass, while the system is fragile on the tail. So if you want to picture this system with in a comprehensive fashion, you need somehow to study it in a simple way. Glass is very difficult to be treated because atoms have a disordered position, so it is different from the crystalline case, in which you just need to know the position of the individual atoms in order to construct the whole structure. For a glass, you need really the position of the single atom in order to reconstruct the structure. So you need a very large S vector, which is a very large S vector, which is containing all the coordinates of the glass. And so to simplify, you can imagine a configurational coordinate, which is just a 1D projection of this S vector. And you can imagine to follow over time the behavior of the glass as a function of time. So you will see that the glass will be something which is placed in one of the minima of the potential energy landscape, while the crystalline case is the deepest configuration, the one with the lowest energy. And if you want to, if you follow the behavior of the glass over time, as it is a metastable state, it will be moving from one minima to the other. And you have phenomena connected to this movement, which are named as aging, rejuvenation, alpha relaxation, or beta relaxation. In particular, beta relaxation is the movement from one minimum to the close one, and alpha relaxation is a movement from one minimum to the regional minimum. So why I'm saying all this? This is because to study glass, you really need not only the position of all the atoms, but you need also the to study the story of the system. So that is the dynamics. So the physicists, they try to simplify things, have imagined a way in order to study this with a simple observable, and this observable is the F self. So you have, I don't know if you can see the pointer, you have this function, which is actually a function of two pictures of the glass at different time, and this F self function is just the degree of similitude of these structures as a function of time. So if tau is the distance in time between the two photos, if the structure of the glass is exactly the same at the two instants, then you have F self equal 1, while after a long time, if they are different, the F self is 0, and in the mean, you have a proper normalization of this observable, so you have all the degrees of freedom, and the F self is falling from 1 to 0. If you have a glass, then you have a typical decay time with different, more than one time. So you have here alpha and beta relaxation, two different decay time, but in a glass you can have a hierarchy of falling relaxation times. So to treat all of this is very difficult if you want to treat this let's say the structured glass system, but so we found as physicists, physicists have found a toy model in which this system can be treated in easier fashion. So you are going to spin. In particular, one of the first spin model is the Ising spin. So you treat your atom as a atom that can have just two coordinates, the upward coordinates and the downward coordinate, because actually the atom is an arrow which is pointing upward or downward. And in the first, this model has been developed to study ferromagnetism, and in particular where we have many domains in which magnetism can be aligned or counter-aligned. And the first model were studying this spin system with interaction on first neighbors, but then there has been a generalization, which is several papers in the 74 from Edward Anderson, in particular the model from Sherrington-Kirkpatrick, where the interaction were more complex, and in particular in the model of Sherrington and Kirkpatrick, the interaction between all the spins was not only limited to the first neighbors, but with the one of a single spin with all the others. So all the spin have been completely connected. And the interesting feature is that in that case, you can have a structure in which at certain temperature, the spin are not all oriented, but they are frozen in random configurations. So this is interesting because with a very simple toy model, you can really tackle different physical phenomena that are very difficult to find in complex systems, such as non-exponential relaxation, absence of self-averaging, ergodicity breaking, ultrametricity, frustration, and moreover, complexity. Complexity, very important parameter. It is an observable which is not qualitative. It's really the number, the amount of minima that you have in the potential and the energy landscape. And this system are very interesting because you can treat, you can study spin glass to model all the system which you have an agent which is trying to make a decision looking at the opinion which is in all other agents. Like, for example, in a stock market, you want to sell or buy actions looking at what all the other people are doing. So spin glass is very useful to make stock market prediction, opinion making, pattern recognition, circuit wiring, packing of object, or airline scheduling. So Another thing about spin glass is that the nobility of this system is connected with the great elegance of the mathematical solution that you find when you solve this system analytically. There has been a huge literature about that, many scientists are studying these systems, but when even if you find a very nice analytical solution for your spin glass system with a very beautiful mathematical elegance, you want to simulate them in order to prove that this theory is connected with the reality. And there is no way to construct a spin glass materially, so the only way to do it is simulating them numerically. So in a very the most popular kind of simulation is a Monte Carlo simulation exploiting Metropolis algorithm. So Metropolis algorithm is based on the idea of flipping a single spin, then looking at the interaction of the single spin with all the others, and then I don't know if you can see my pointer.
No, not yet, not yet. We cannot see actually.
Okay. Okay, I cannot do it now. In each case, it's the second step in which you can calculate all the couplings, and so you have to calculate a number of terms which is dependent on the number of spins that you are considering, and then you retrieve the energy variation. And to do this, you follow the Hamiltonian, which is described by the Sherrington-Kirkpatrick, in which this S vector is the orientation of all the spin, and you have a JJ matrix, which is the coupling between one spin and the other. So what we want to do optically, we want actually to then after this this simulation, you have to make a decision if to accept the movement made by that has been tried, and this is done with the probability 1 if the energy is decreasing, or is accepted with a probability dependent on temperature, is instead the energy is increasing. Otherwise, this is refused. And what we want to do is optically replicate this system. And this is made exploiting several optical elements or optical effects. So we have a laser, which is a coherent beam, so it's a flat wavefront, which is impinging on a digital micromirror device. And so we are approximating the wavefront of the laser are completely flat, and the intensity is the same on the wavefront. So the laser is impinging on a DMD, and the DMD is dividing this wavefront in many light rays. Then each light ray is going through a turbid medium, and so each light ray is dephased and attenuated of a random amount. Then you have retrieve the energy variation by looking at a camera on a given pattern. So in a given point. So why this is equivalent to perform a spin glass simulation? This is because you have you can index your light ray with the S vector, and so each light ray is representing a spin, and the state of the spin is equivalent to the state of the DMD. Then each light ray is passing through the two-probit medium. So you have that there is a transmission matrix, and what the transmission matrix does is to attenuate and dephase each light ray. Then you have to retrieve intensity on the camera, and the intensity on the camera is just the multiplication of all the contribution from different light rays. So you have to sum all the possible combination. So you have a sum over two indices in which you have each value of the transmission matrix of the disordered material. So in the end, the intensity, if you approximate the intensity of the laser as 1, identical for each element of the DMD, then intensity on the camera is just proportional to the matrix element VEJ, which is the multiplication of two different light rays outgoing from the DMD matrix. So this is in the case in which the DMD matrix is completely flat and placed in one configuration. But if you put your DMD matrix in a random configuration, then you have to multiply this V matrix for the S state of the DMD, and thus you have two contribution from two multiplied light rays. You have the two values of the two different values of the S vectors. So if you compare the intensity measured by the camera with the Hamiltonian of the spin glass system, this is actually the same. So the way we describe the intensity on the camera is exactly the same as the Hamiltonian of the Sherrington-Kirkpatrick system. So we have a method in order to really simulate by measuring optically the Hamiltonian. So actually, I have to make add a detail because I imagine that all the people that are expert with DMD will be raising their eyebrow, because a DMD is actually capable. It is a digital micromirror device, so it's a structure which is made of many mirrors, and each mirror can be tilted in one direction and another direction. So you have just in principle two possible steady position. And so you can actually, the DMD provides the S in the configuration 1 or 0. So you can turn on the light ray or turn off. So in order to transform it in a +1 or -1 configuration, you have to make some adjustment. In particular, you use this very nice approach from Jacopo Bertolotti and others in the reference below. You have this superpixel-based method in which you put a filter, a spatial filter in the conjugated plane of the DMD, and you put it in a precise location, cutting a set of the outgoing spatial vector from the DMD, and then you can merge the DMD into superpixel. These are also called segments. These in our case are 4x4, 2x2 pixel superpixel, in which you use just two configurations, the diagonal one. And in this case, if you do all the calculation, I can convince you that the DMD is capable to give you light rays multiplied by +π or -π, which is equivalent to the +1 or -1 configuration apart proportionality factor. So this is the whole setup. This is the DMD. The DMD is reflecting the light for all the pixel which are turned on. Then you have a relay system with the iris, which perform the superpixel method. Then you have a opaque medium, which introduces the random transmission coefficient, and then you image this opaque medium on the camera. So we have the possibility then to simulate the spin glass, and to do this we also need to do a loop, because a Monte Carlo, if you want to do the dynamics with a Monte Carlo simulation, you have to repeat this actuation, these changes in the system many times to follow the dynamics. So the spin flipping is mirrored on the mirror flipping. Then you have the coupling calculation, which is performed by the disordered material, the intensity measurement, which is the correspondent to the energy calculation, and then you have to accept or refuse the movement, and this is done by numerically on the digital layer, accepting and calculating the metropolis probability, and accepting it by or refusing it by updating the DMD configuration. So we have a loop out of this, and with this we are capable to make our simulation. So we repeat the Monte Carlo simulation many times. Each time we store the state of the DMD, and we can calculate f self just by multiplying the two configuration, and then we can do this at a different temperature just by controlling the T parameter, the beta parameter in the probability of acceptance step. So we can perform many optical simulation as a function of a temperature, and actually this is the first result. in the figure A, you see, but this is not what we was expecting, because the F self is flat. This is not what we were expecting when you have a disorder at the system, a spin glass system. So you expect a double decay typical of the spin glass. So we continued, we performed further experiments, and in particular, we made many fast simulation at zero temperature, and we retained the final configuration. And then we constructed this figure on the side, the two squares. This is representing the overlap, the degree of similitude of all the solution we get with respect to all the others. So on the diagonal, you have always one, and then you have all other pairings. And you see that we have, this is divided into squares, which are all very similar and very, and are antisymmetric. You have -1 with the other configuration. So this means that you have just two states in your system. And this is connected, somehow expected if you have, as we are measuring intensity, and so any spin configuration will be, if any spin configuration is a state, then also the spin reverse configuration also is a state, because this the minus configuration with respect to the other. But we were expecting to have much more states, so we are going through investigation about the system. And actually, we came back at our Hamiltonian, at our V matrix, and you can see that the V matrix can be written as a multiplication of two different psi vector. So actually, we can write our psi matrix as a, and our Hamiltonian, our intensity description, as a vectorial product of the psi vector, which is the transmission matrix, and the S vector, which is the configuration of the DMD. So this is saying us that if you want to improve the intensity in one location, you have just to align your DMD matrix to the psi matrix, which is the transmission matrix of the system. So this can be done, it's an n-dimensional problem, but you have just two directions which work, which made the job, which is the psi direction and the minus psi. So for this, you have just two solutions. And the system is not complex. So to add the complexity to the system, what we change is to study to look at, instead of intensity, to look at the sum of intensity of many points on the camera. In this case, the single element of the V matrix is instead the sum of many V matrices. So we construct this J matrix, and we construct an effective intensity Hamiltonian in which you have the JJ is just a sum of different transmission matrix at different point. And if they are placed at a distance which is larger than the speckle size, this transmission matrix is uncorrelated. And so we restore the expected JJ, which is completely Gaussian. So indeed, you find the complexity in the Sherrington-Kirkpatrick model. To find the complexity, you need that the GEJ matrix for the coupling to be a Gaussian with a random Gaussian distribution, while we are constructing our JJ matrix from a single vector, the transmission matrix multiplied by himself. So there is a strong correlation in our matrix. We were studying the correct Hamiltonian, but with the wrong matrix. Adding many maxima, we are able to study a matrix which is very similar to the Sherrington-Kirkpatrick one. And in this case, you find the F self have this very nice double relaxation time or more decay, and you see that the Q matrix on the right, is fragmented in many maxima, the square that you see, which is the case that you expect when you have a glassy system. Many minima of the many states of the system, many minima. So just a further confirmation is about the complexity of the system. We study the P of Q, which is an observable which characterizes the state of the system. The Q is the degree of similitude of one state with the other when you perform many replicas of the system, which is many simulation with the same disorder but different starting configuration. And you find that when beta is small, that is at high temperature, you have that the system is in the paramagnetic state, because you have a single minimum of the Q, single maximum of the Q around 0. Then when you lower the temperature, the system splits into minima, which are the two ferromagnetic states. The system is going in the ferromagnetic states, which is one and the opposite of the other. So you have plus Q and minus Q. When you start to increase the P, the number of targets, then apart from the 2Q system, you have also a maximum in the center, which is connected to the onset of the spin glass system. So this is further confirmation that this is a spin glass and we are simulating it optically. So the last slide is about the speed of the system. So this is the F-self simulation that you see here is the largest simulation that we have performed, which has been done with 12,000 DMD elements, 12,000 DMD segments, and with P equal of 1,000. So in this case, this is a very large simulation. This is optical, so it takes a lot of time to thermalize, and this required days for each temperature. And this, you can see here about the speed of our simulation, our simulating system. You see the time per step, the step that you need, the time that you need to make a Monte Carlo loop step, that compared for the digital simulation and the optical simulation. So you see that the digital simulation, the time is proportional to n, because you have to calculate the contribution of each spin coupled with all the others. In our case, the coupling constants comes from the light which is passing through the disordered system. So it's computed at the speed of light, really, by the passing of light through the disordered system. Actually, our bottleneck is the DMD rearrangement speed and the camera acquisition time. And you see that the digital time, even it starts faster, the digital calculation time, the time per step is smaller, is increasing linearly with the number of spins, while the optical case is flat, because you don't need to increase the time with n. And so we beat the digital simulation at n equal to 1,000. And this is not the maximum that you can reach with our DMD. Actually, we can get at least 10 times this number. So just to recap, this is my talk has been about an optical simulation of a spin glass dynamic system, and this has been done by exploiting three elements: the DMD, the turbid medium, and the camera. Then we constructed a loop by putting all these elements in a optical optical layer coupled to a digital layer. Then we demonstrated the spin glass regime when you increase the P parameter, that is number of targets on the camera. And then we demonstrate the capability to beat the optical cycle for a large N. I would like to thank all the collaborators to these results, which is Giancarlo Rocco. He is the director of the Italian Institute of Technology. Actually, is the guy who had the idea to couple of the correspondence of the intensity in a wavefront shaping experiment with the Hamiltonian of the spin glass system. Luca Leuzzi, which is the theoretist, which have performed all the analytical calculation of our system, which is slightly different from the Sherrington-Kirkpatrick model due to the how the JJ elements are constructed. The student Eric Corman, which is a wonderful student which has been capable to construct all the simulation and optimize all the simulation digitally. And then last but not least, Giorgio Parisi, which is one of the father of the study of the spin glass in Italy, one of the best Italian scientists, and I'm really proud that he has been collaborating with us in these results. So thank you very much for your attention.